All right, I'm back. I am just going to turn back on the banner, letting people know that I'm doing this right now. Oh. And I will wait until I'm. There we go. Okay. And yeah, let me just adjusting. So basically, where I'm at right now, I'll just show you guys. I've got a little sheet here. So I have made. I finished first pass, just in case this is you're just tuning in and you haven't been following the project. I have done all of the lectures, so I've watched all the lectures at least once, and I have now done all the problem sets first pass. The problem set was quite difficult. I think if I had been getting most of the questions right with some time and thought on the problem set, I would probably be ready to write the exam, but I went through and I would say most of the questions I didn't get right off the bat. Quite a few of the questions, I had no idea how to solve it. So there was a considerable number of questions where I'm just staring at it and I'm like, nothing's coming to me of how I'm supposed to be solving this. And I mentioned some of the possible reasons for that. One of them being that this is a challenging class for me. Another being that if I were actually an MIT student, I would have likely have done recitations on this. The problem sets would be meant to be, discussed with your friends and that are in the class and things like that. So if you're struggling with something, they might give you a hint. You can work through it together. Basically, the problem sets are supposed to be hard and they're supposed to be challenging and push you through. Because I don't have access to that environment around me, the solutions to the problem sets are kind of filling that role. So rather than treating them like regular homework assignments where I have to get them perfect to get a good grade, I'm kind of treating them as that opportunity for practice that I think that they are intended to be so in MIT, but it's just a little bit of a different choice because I don't have the grade as an incentive. I'm using these as a learning opportunity. However, the disadvantage of that is that it means that I've gone through all the material and I don't have any more feedback material other than I do have some questions in my textbook, but I don't know how relevant they're going to be in terms of comparable difficulty, comparable techniques for the exam. So with that in mind, now I have several days left and I'm trying to decide how I should spend my time. So yesterday, after I finished all the problem sets, I spent some time going through and I made a list right here. I'll put it down here so you guys can see. So I made a list that went through each of the problem sets and identified any concept, technique, or fact that prevented me from answering a question right. This is not a perfect list. Sometimes there was a really isolated trick or fact that I didn't think was general enough to include. There were other times I didn't include it because I felt like after I got the answer, I understood it. So there's nothing more to practice there, even though I didn't necessarily get it right the first time. And this analysis here, plus going through some of the lectures. So I went through my lecture notes and jotted down places where I had made notes when I was doing the lectures the first time that I didn't feel like I fully understood it. And so that led to a more condensed description here, which basically has two parts. So the top part here is a redo or a second pass of the problem set with isolated problems. So the ones circled are ones that for whatever reason I didn't actually do the first time around. I think for these first ones here, the majority of these ones were because I didn't actually have access to some of the like you needed to have an applet running and I didn't think I had Java installed and I didn't want to waste time downloading Java, installing it, restarting the stream, this kind of thing. So I just skipped them when I was doing those. So those I can do fresh. But the rest of these are ones that I have done and I didn't get right. And I would like to try them again. And I'm hoping that not only having done them once before, but also the knowledge I've gained working on the other problem sets, the feedback I've gained, and also hopefully some work I'm doing now on some of these other weak points, I will be able to get them, or at least get a lot more of them right than I did the first time. And this is a limited sample, so it's not every question, but they were ones that in particular I thought had concepts that I didn't fully understand, or that the derivation involved some technical methods that I wasn't able to execute in that time. And I'm hoping that coming around can do them. Now, there's a risk of doing it this way. One risk is that you will just remember the answer to the problem or remember how to solve the problem. So I have done a lot of these problems. Some of them I'm probably going to remember, oh, right, I was supposed to do this to solve it. That's not the end of the world, but it isn't ideal if you're trying to work from principles rather than having memorized certain things. I talked about this yesterday, where I have this kind of analogy. I'll just show the little drawing I did here. But basically, you can imagine, if we look at it this way, you can imagine your problem sets as being some sample of the full possible problems that you should know how to do as a result of taking the class. And then this is some sampling of those problems. Now, the exam itself is probably going to be some smaller overlap here, like this, of these problems. Now, there's probably going to be problems in here that won't be on the exam because they're too difficult. There's also, because you can make trivial adjustments to it, you can have problems outside of this that could be on the exam. So now I was saying that the key thing when you're talking about practice is how much of this surface is within this set. So does this set hold, like, is this almost the same as this, so that you practice literally everything that you would need to know as possible problems? Well, in a physics class or mathematics class where you can make slight tweaks to questions and they're you're still expected to be able to solve it, my guess is that this is actually a smaller subset than 100%. And so if I just master these problems, I am going to get better at this subset, but I'm not necessarily going to get better at this subset. And so it's possible, if this is a very small subset, that you could spend hours and hours and hours and hours practicing those problem sets and not actually increase your final grade that much. In contrast, if this is most of the area, then the better you get at this, the better you'll get at the actual test. Another example I was saying is that this is just sort of one layer of just considering it as a two-dimensional thing. But the other way is to also think about it in terms of specificity of what you're doing. So at the high level here, I have principles, and at the bottom level here, I have answers. So these are principles of problems, and then there's concepts, and then there's specific techniques that apply to particular problems, and so on and so on and so on. And so if you look at concepts, my guess is that the coverage of the problem sets is almost 100%, if not 100%. There's unlikely to be any problems that will be done on an exam so this is 100% coverage nearly here. But of course, just knowing these principles, it's very difficult to actually derive answers without some kind of practice. So I need to work down lower layers too. And so the opposite of that is just memorizing answers to particular questions, which is obviously not right either. So I'm trying to find some middle layer of abstraction that is specific enough that it's workable, that it's learnable. But on the other hand, it's general enough that I'm not really fine-tuning for a very specific problem that I'm unlikely to encounter on the exam. So with that in mind, I made a list of things that I wanted to improve. And I've been doing some Feynman techniques on it today. So some of the things that I've done today is I did dispersal relations for waves, which was from 803, a class I didn't do. So I actually downloaded, I should put it over here so you guys can see. I actually downloaded a lecture from 803 that I hadn't watched and put it up there just so I could see what this thing was about. And it was kind of how I was expecting, so I didn't really pay too much attention to it. I don't think it's going to matter too much, but still good to know. I also worked through some stuff from 1801, so just regular single variable calculus, refamiliarizing myself with the logic behind Taylor expansion, integration by parts, substitution of variables, and so those were some things that I was also working on. I also made a few flashcards. Now, I'm not sure what I'm going to do exactly with these flashcards. I started making them out, and then I realized just finding all of the things associated with the flashcards itself is going to be challenging. So even to just identify all the things. So what instead I did is I made some of these little flashcards and pieces of paper here. And then what I'm going to do is, as I go through problems, as I go through things and I identify, oh, I should really have this memorized, I'm going to put these on flashcards. I try to not use flashcards for these kinds of classes. The only reason I'm doing it is because there was some stuff that showed up of like, you should just know this. And so I wanted to make a few flashcards, but generally I avoid flashcards for a couple reasons. One, I have this formula sheet. This is the formula sheet that's going to be on the exam. There's quite a bit of stuff on here. So there's not that many things that are not on this formula sheet that I would need to know. So like it has, for instance, Planck's constant, mass of an electron. You know, it even has the speed of light, which I feel like if you've gotten to this point in physics, you should just know that it's 3 × 10⁸. But I did want to put some things on there. Generally, I don't go too much with that just because I feel like it's not super valuable. But there are a few things that I thought might be important here, particularly trigonomic identities, as well as eigenstates of some of these energy eigenstates, or in the 3D case, angular momentum eigenstates of some of these problems that we've studied, which again are not on this list. Some of them are on this list. I mean, they have spherical harmonics. They have a few things on here, but not 100%. So I do maybe want to practice those a little bit, but going through the book and trying to peel out those exact things without overdoing it and making 100 flashcards I don't really need to memorize is going to be challenging. So I think I'm just going to do it while I do these problem sets, that if I identify a fact that I need to know, I'm going to just put it on there. And I don't think I need to go through these flashcards too many times, but if I did it a couple times in the next few days, I think it would be fine. What do I want to do now? Now, when I left off, I had identified a few things that I thought I wanted to do that are kind of small Feynman techniques, meaning that they are not they're not particularly substantial. There's not a lot of stuff that I need to do here for this. And there's also some that are, this should just be something I don't have to look at a lot of lectures. And then there were three ideas which corresponded to roughly 4 or 5 lectures in the class, which I didn't feel like I had a great grasp on. Now, I don't know whether I want to watch the whole things again. That might be a little bit tedious. But I definitely felt like the identical particles argument, I only sort of understood. The angular momentum eigenstates and values. This is probably similar to this is something that I wanted to have a better visual intuition for what does the angular momentum eigenstate look like. So I can probably piece out a small part of the lecture. And then the periodic lattice and the crystal momentum was something that I also was a bit fuzzy with. So I might go over that again. So I think I'm going to work on this today. If I get any more ideas of stuff to add to my flashcards, I will, but I don't have any right now that I want to add. And then I'm going to work on this for the rest of the day. And then after this is done, I'm going to, so I'm going to take a weekend break. And then on Monday, I'm going to be back and I'm going to be working on these problem sets. And I think my plan is I'm going to do problem sets in the morning and Feynman techniques, conceptual stuff in the afternoon, or like additional practice or things like that. And I think if I go through it, this thing, I can probably get this done by, I should be able to get it done definitely sometime next week. The promises were taking a lot of time in the beginning, but I'm hoping the second pass will be a little bit faster. But, even if it is slow, I should be able to get this done by Friday. Then I have Monday, Tuesday left in April to work on this. And I'm hoping that Monday, Tuesday, I can work on some stuff for preparing for the exam. I only have one exam, and unfortunately it's not from this session. And I don't know whether that's going to be a problem. I haven't looked at the exam. Part of what I, when I was doing the MIT challenge was to not look at the exams before I did them, because otherwise, if you know what the questions are going to be on it, you can very easily tune your studying to it. So I didn't look at the exam, so I don't know what's on it. And that might mean that they cover things that are different from this class. I'm hoping that's not the situation. I did have that happen a couple times in the MIT challenge. It usually wasn't a problem, but with a class like this, which is very challenging, it could also be that if you change, like they use a different notation for a certain problem and I'm not familiar with that notation, I might not be able to solve the problem, even if I know a lot of the underlying principles. Or if they decided to focus on a different subset of problems. So we did this sort of whole periodic lattice and crystal momentum. Maybe there's a different subset of quantum physics problems that can appear in 804 that I have not covered. I don't think that that's going to happen, but it's always a little bit worrying. I do have midterms and a final exam without solutions for this session. So what I might do is I might save those, and then if my attempt at doing the one with the solutions is really botched, I might keep those around. I won't be able to get feedback on it. I won't be able to know how well I did to the precision of a grade. But I mean, for a lot of these questions, you can know whether you've kind of roughly got it or not. I mean, a lot of them, if you don't know how to do it, you just have no idea how to do it. Whereas, if you've got kind of the right answer, it usually works. I mean, unless you're kind of, it's just says, I'll just say this, even though I can't show it. All right, with that in mind, I think I want to move over to some of these ideas. So let's just start sequentially in this list here with delta function normalizability. Now, this was something covered specifically in a class. So I think I'm going to just, what I've been doing with these Feynman techniques is, let me just finish writing this first. I find it very hard to talk about one thing and write a different thing at the same time. So one of the things I've been doing with these Feynman techniques is I have been focusing on first trying to do my recall understanding of what the concept is and how it works, and then going to the source. I don't do this if I have no idea. So there's not much point if you just, I was really confused about this, so I have to go back to the source. But for something like this, where I have some sense of it, but I don't feel like it's a great sense of it, I'm going to put what I think first. And this is good for two reasons. One, it practices active recall, so I'm going to strengthen my memory of recalling what it's all about. And sometimes something is confusing when you really sit through and you try to do the Feynman technique, it actually makes sense. So big reason for doing this is that once you do it, sometimes something that seemed confusing actually seems trivial at the end of it. A lot of the ones I've done, it's like once I start doing it, I'm like, oh yeah, actually this is pretty easy. It's not actually that difficult. And then the other reason for doing it this way is that you also identify your mistakes. So if you just watch the lecture and you didn't do it first, then sometimes you're copying their answer without figuring out what was the thing you didn't understand about it. So when you're trying to do it and you're kind of screwing things up a little bit, and then you look and you're like, oh, that's why you're supposed to do it this way. So if you, I'm going to try to upload these notes later. There's a hell of a lot of notes, so I'm not sure exactly how I'm going to scan all of these things. But if someone from the future is looking through some of these notes, these Feynman techniques, they're going to notice some of my Feynman techniques are wrong, or they start off wrong. And the reason why is because I'm doing it this way. I'm trying to recall and then check. And so that means sometimes I write down things that turn out to be inaccurate. So these are not supposed to be taken as teaching guides for someone who does not know it. This is meant to be a learning technique for me. So what is a delta function normalizability? So we have harmonic planes cannot Shouldn't use lambda here. Let's use okay. Little reminder here about what it means to be an eigenfunction. Hi, Armel. All right, so let's look back and see where we did delta function normalizability. That's all I remember. Let's see if I can look up a Wikipedia definition, because it's going to take me a little while to search through my notes here. Hmm. This is hard to search for this. Delta function normalizable. Or the limit of a sequence of normalizable functions. Where did they talk about it in the class? Have anything here? No. Do I want to find this? Yikes. All right. I'm going to just switch back and look through my notes here. It's a little hard to Google search because normalizability and delta functions both exist kind of separately. So this delta function normalizability is kind of a hard idea to search for on its own. But I do remember it being talked about in the class. You know what? Maybe I can search for it in the transcripts, because I know he says that exact term. So maybe I can find it there. 8, 4. What am I doing here? I should go here. All right. I don't think it's going to be here, not here. No, not here. Where would it be? Let's go. I'm going to try going from a 15. No, let's go. Let's try scattering here. Okay. Okay. delta function normalizable? So it definitely talks about it here. About halfway through. Oh, here we go. These are normal. Okay. Question. This is right near the start. All right. This is lecture 12. And I don't want this. I want lecture 12.
The following content is provided under a Creative Commons license. Your support will help MIT.
Or eigenstates that are strictly localized in some region. For example, the infinite well, all the states are strictly localized to be inside the well. In the finite well, as we saw last time, there are a finite number of states, energy eigenstates, which are bound inside the well. But there are also states that aren't bound inside the well, as you'll see in our citation. And as we discussed in the qualitative structure of wave functions, but energy eigenfunctions. So, why do we really care about the opposite order was next down? So why would we really care about states that aren't bound for scattering states? And the obvious answer is, I am not bound, right? And most things in the world are either bound or they are scattering states. A scattering state just means things that can go away, things that can go away. So, it's often, it's easy to underemphasize. It's easy to miss the importance of scattering experiments. It's easy to say, look, a scattering experiment is where you take some fixed target and you throw something at it, and you look at how things bounce off, and you try to do something about this object by how things bounce off. For example, one of the great experiments or day is the LEC, and it's gigantic.
Can I figure out exactly where this is so I don't have to look it up? Delta function. Okay. Do we have interactive transcript here? Delta. Which time is this? 5. Okay, 5 minutes.
Fantastic question. Okay, I'm going to come back to just a second. It's a very good question. So we're interested in energy eigenstates, and we know the energy eigenstates for the free particle. We've written these down many times, and I'm going to write it in the following form. Suppose we have a free particle in an energy eigenstate with energy E, then we know it's a superposition of plane waves e to the I kx plus b e to the minus I kx. And the normalization is encoded in A and B, but of course, these are not normalizable states. We typically normalize them with 1 over root 2 pi for delta function normalizability. Now, in order for this to be a solution to the Schrödinger equation, we need that the frequency, or the energy E, is equal to h bar squared k squared upon 2m.
Damn. Thought he was going to explain that. I'm just going to do let me switch back over here. Oops. Let's just switch back over here. Okay, here we go. So hold on a second.
So more precisely, what we usually do is we say e to the I, we take our states phi sub k equal 1 over root 2 pi e to the I kx, such that phi k prime is equal to delta. Sorry, this is what I wanted to write. Such that, well, phi k prime is equal to delta of k minus k prime. This is as good as we can do. This is as good as we can get to normalizing. It's not normalized 1, it's normalized 1k is equal to k prime to the value of the delta function, which is ill-defined.
Okay. All right, let's see if I can parse that now. I think that's about all I'm going to get on this. So. What was it? Delta k minus prime? Is that it? K prime minus k? So let's see if we can show that. So this, of course, is negative infinity, positive infinity. Now we're taking the complex conjugate. Okay. To remember what our Fourier transform is. Where's our Fourier transform? So our Fourier transform. All right, that was a little less edifying than maybe I would have liked, but I think that's about as much as I can do, so I'll just cross that off. Let's do real energy eigenstates. What is the energy for this? This is h bar squared k squared over 2m. Hi, Hyped Studios. Yeah, I'll do it here. How do I show that this is? So I think you can take. It's momentum over 2m plus. That should be. I don't know if, and then this was. All right, let's switch pencils here though. And then this would be E energy equal to so we're going to do one derivative. We're going to have A prime x e to the I psi x plus should be psi x e to the I psi x plus I psi x e to the I psi x. And then this is going to be A prime prime x e I psi x. Then we're going to have looks like it says ax. Then we're going to have and this taking derivative again, we're going to have, oh, this is a three-part thing here. So let me write that out. That's going to be derivative of this with respect to this plus each one. So we're going to have three things. So this is going to be psi prime x I x plus, we're going to have another one drop down. We're going to have minus psi going to have psi squared x e I psi x ax. And then finally a and I prime Yes, it's going to be tricky to copy down. Can I reorganize this some ways? So I can cross this one out and put 2 times this. So I have 4 terms. I'll write it over here so I can see more easily here. A x I y x. Now we want to consider how would all of this now my idea was to have a wave going in the opposite direction. Now, is this right? Let me consider this closely here. So first we're taking these two derivatives, except this one's going to stay the same. I'm going to just write it out here, so I'll just do it slowly. So now we have a bar x prime e to the minus I psi of x, and then we're going to have like that. Oops. E to the minus I psi x. So this will go down to a double prime x e to the minus I psi x. And then this one is going to go to, we're going to have 3, then we're going to add another one here. So we're going to have this one is going to be minus I theta x a prime x e to the minus I theta x. And then these ones are all going to be here. So we'll do derivative, I'm going to call this 1, 2, and 3. So 1 is going to be minus I theta prime x a x e to the minus I theta x. And this one is going to be minus I theta prime theta x a prime x e to the minus I theta x. And then 3, we're going to have, drop it down 1, we're going to have plus minus I, then I are going to cancel, so it's going to be overall minus sign theta squared x a x e to the minus I theta x. And then we're going to have plus vx ax e to the minus I theta x. This is going to be I have minus 2. Yeah, minus I. So I should have the right value here. And the question is, do these give the same value? doesn't look like the same energy, but that was the idea behind it. And these differ. Let's do them with the pen here. Here and here and here and here are different. That's where the minus sign comes into play. Well, I thought those would cancel and we would have just the same stuff. Here at the top, but we don't because we don't take all of these terms. So let me see if I can go back to the problem set where we did this. So let me look here. I don't remember which problem set that was. I think it was early on. So this is not the proof that I was looking for. So it is saying hint beta x. Oh, making a noise here. Theta e of x. Complex conjugate. So let's try working this out again. So this would be the meaning of an energy eigenstate. This just returns a value. I want the star there. I'm going to put the star here. All right. Can I do this? I think that helps me. I don't actually know what this is, so maybe I don't want to do it that way. That also seems to be the wrong way to do it. Trying to think hard now about what. I mean, these are linear operators. So I think the idea is that we do E. I feel like it's the fact that this is all powers of 2 derivatives going to be important. It doesn't seem to me clear that you could always construct a purely real momentum. I don't think you could do this with momentum, so it can't just be the fact that these are linear operators, because if you had momentum, yeah, I mean, a purely real one's not going to have, it's going to have net zero momentum and that's just a single derivative. So it has to exploit the fact this is a double derivative. So we're like dropping the I. Oh, okay, I think it's, so I think it is real theta, right, plus I and theta. And then this is going to be E. I'll do so this is E, and then we can go minus E. No, I don't need the complex conjugation anymore. So this is unchanged. And this one here, we're going to have take the derivative of this twice. Get the I twice. I guess I can just put this here. But then this one doesn't do that. The hat on the E means that it's the energy operator as opposed to a variable. So an operator is a thing that takes a function and gives you another function, as opposed to something that a function, for instance, it takes a number or a value and gives you another value. This is saying, take this whole thing, this theta E, which is itself a function. It maybe looks like this or something. And give me a new function. And in this case, we're looking for energy eigenfunctions, and these have the property that when you apply this operator to it, you actually get the same function just to some scale factor. So these are important things to study because the operators in quantum mechanics correspond with observables. And so in this case, the energy operator, when applied to certain states, will give a particular energy value all the time. And these energy eigenstates correspond to states that have definite energy. I mean, it will depend exactly on the system of what potential you have, depends on what those shape of those things are going to look like. And here I'm trying to show that you can always take these states to be real, even though wave functions are in general complex valued. And I'm struggling, and I know it has to do with the fact that this is a second order derivative and a 0th order derivative is key to this, and I'm just missing what's going on here to make the math work out. We get minus IM and we do this twice, what happens? I think we get minus IM again. So this just goes back to minus IM, which goes back to our same. I'll just put E. So I think it's that we have minus I bar f of x squared dx squared is going to be, well, see, I don't see why this is, this is just going to be, it can't just be that this is a linear function. Yep, I'm going to go to the answer and look it up. What do we have? This is problem set 4. Okay. Where is its explicit form? Yeah, why is this the case? Because if we just had a single derivative, I don't think it would work. Why does it work with 2 derivatives but not 1? Well, I think the idea here is this is a double order derivative, and I think that there might have been a lecture discussing this, but the basic idea is that if this were single order derivative, it wouldn't necessarily, this is necessary, but I'm trying to figure out why the complex value is changing this way, because when I'm doing the math, I must be screwing something up, because real function minus I, imaginary part of the function. We take the double derivative of both. They don't change. But I mean, if you were to do it with a single derivative, I don't think it would work. But it looks like it would work from this. Let me just check the lectures to see if there was some mention of this, because I seem to remember it coming up. So this problem set 4, let's look at the calendar. When would problem set 4 have hit? Would have been due here. So it must be around lecture 8. Maybe more on energy eigenstates. See if they have, I'll do it from here.
Additional materials from hundreds of MIT.
Not working. Ba, ba, ba. Yeah, well, the thing Samatan is suggesting that I try this out with the single derivative, because the idea here is that there's some facts I know about this problem. So I know for a fact that the momentum operator is minus I h bar ddx, which is a single spatial derivative. And we know that this right here, e to the I kx, and then you have e to the minus I kx. These are both both eigenvalues, or these are both eigen states of momentum, but one you're going, this one is going this way, and this one is going this way. So they're going in opposite directions. So they have opposite momentum. So if you add them together, if you have e to the ikx plus e to the minus ikx, so you add these conjugates together, you don't get a purely real momentum eigenstate. You get a standing wave, which isn't moving at all. And so this is what we are able to do for energy, but we're not able to do for momentum, is that in energy, these two have the same energy, even though they're pointed in same directions, but in momentum, they're pointed in opposite directions. So we can always take our movement components and sum them so that we get a standing wave, which is related to the fact that the energy eigenstate is stationary, or it can be made to be stationary, so that it's not moving. It has fixed energy. It's staying stationary. And so the challenge here is that this is related to this being a second derivative, but I'm not sure how to prove that in the math, and that's what I'm working on right now. I'm going to go over my notes here to see if I wrote it down, because I think he discussed this in the class and I kind of glossed over it, because it was like, oh yeah, it's because this is a second derivative. But now that I'm doing it, I'm screwing up the math, and I'm not sure why, because I'm looking at it wrong, I think. Quantum has 3 states. I'm not sure what that refers to. Where? It would have been around here.